Okay, so this is going to be the next lecture of Riemann integral, guys. So the next in the previous lecture we were discussing problems related to Riemann integral, right? So we are going to continue discussing the problems on Riemann integral. Then we will be moving on to certain theorems related to Riemann integration. Oh, so the first problem, it's one of the most standard problems from the concepts of Riemann integration, is that show that show that a constant function k is integrable, so that a constant function k is integrable on the closed interval ab, and integration a to b f dx equals k times b minus a. Okay, solution to this problem is pretty simple. So you're given a constant function, right, k. Clear? So you can take say any partition. You can take any partition a equals to x0, x1, x2 till xn, which is equals to b, let's say, where you have ir is equals to xr minus 1 to xr, and so you have delta r equals to difference between these, the endpoints of this interval, right? Okay, now the thing is that if you define mr as the glb of f in ir and capital mr as the lub of f in ir, let's say, and so from here, see, and if you also define m as the lub of f in I is this interval. Okay, this interval is taken to be I, and small m is the glb of f in I. Now since this is a constant function, and it only takes values as k and nothing else, so it is pretty much evident from here that mr equals to capital mr equals to capital M equals to small m, and all these equals k, right? All this equals k hypothetically, right? Because this is a constant function. It takes only one values, whatever the domain be. So what we used to consider as the greatest lower bound or the least upper bound in some interval, or the greatest lower bound of the function, least upper bound of the function, or each and every value is basically k and nothing else, right? So now if you find LFP, what does it come out to be? Summation r equals to 1 to n. Here you had, so you would have small mr, which is basically equals to k times delta r. So what is k times summation delta r summation is b minus a, so this is k times b minus a. As simple as that, right? It is as simple as that. Similarly, in exactly similar way, UFP will also come out to be k times b minus a. So if LFP is a constant, k times b minus a, UFP is a constant, k times b minus a, so the integration a bar b f dx, which is basically the LUB of all LFPs possible, it will be k times b minus a itself, because LFP also comes out to be a constant. Similarly, the upper integral will also be k times b minus a, which gives you the value of the required integral, which is also k times b minus a. Okay, this was a very simple problem. Clear? Okay, let's check the next problem. So it is quite you people have already done these sort of problems in the definite integration topic. So this is kind of checking of the definite integration problem through Riemann integration. Okay, so you are given the question, show that x square is integrable on any interval 0k, and the integration 0 to k x square dx is basically equals to k cube upon 3. Clear? Clear? Okay. Let's check the solution. Now this solution is pretty simple. Basically just see the steps. Clear? So the function you are given is x square. So first we need to determine the partition which we should be taking. So since this is a polynomial function, so what we can do is that we can take the partition starting from 0, and we can go by an AP, okay, and you can do it like this: k upon n, right, 2k upon n, 3k upon n, till you reach nk upon n, which is basically equals to k. So these are the points of the partition you are getting. So what your IR is, it is basically r minus 1 k upon n to rk upon n, right? And what is your delta r? K upon. It's pretty simple. Okay, it's pretty simple. Now you need to find small mr. Okay, now what should be small mr? So small mr should be basically, see, x square 0 to k is basically an increasing function. Okay, so the image of the starting point of the interval must be your small mr, and capital mr is the end point of the interval. As simple as that. Okay, so you can find the LFP. So LFP must come out as r equals summation r equals to 1 to n r minus 1 into k upon n whole square times k upon n, right? So what you can do here is that k square and n square, this is k cube by n cube, right? You can take it common outside, and here you have r equals to 1 to n r minus 1 whole square. Okay, now r square, in case of r square, summation r equals to 1 to n, you have n into n plus 1 into 2n plus 1 by 6. Okay, so you can use that here as well. I mean, you can, if you just expand this summation, you will find out that this thing basically equals the formula n times n minus 1 times 2n minus 1 by 6. Clear? And this can be written as k cube times 1 minus 1 upon n, 2 minus 1 upon n upon 6, right? Upon 6. Now if you wanna find the lower integral, that is 0 bar to k x square dx, you just can apply limit n tends to infinity to LFP, and if you put limit n tends to infinity here, so this becomes 0, this becomes 0, you are left with k cube by 3. Okay, you are left with k cube by 3. Try the same thing for UFP. So you can do it yourself only. So this comes out to be, you can see it, k cube upon n cube. This is r equals to 1 to n, and here you have r square, right? Here you have r square. So r square, so this will be k cube upon n cube times n into n plus 1 into 2n plus 1 upon 6. So if you take the same step, it is k cube into 1 plus 1 upon n times 2 plus 1 upon n, and if you apply limit n tends to infinity here, this becomes k cube by 3 as n tends to infinity itself. So the upper integral also equals k cube by 3. I'm not writing the steps here, you can write it on your own. So 0 to k x square dx equals k cube upon 3, and it's done. Okay, it's clear. Okay, let's check the next problem. Okay, so question: if a function f on the given interval 0 to pi upon 4 by giving the function as fx equals to cos x and sin x. It's a piecewise function. If x is rational, it comes out to be a cos function, and if x is not rational, it comes out to be a sine function. Okay, so then show that f is not Riemann integrable. F is not Riemann integrable. So this is the symbol of the R indicates Riemann integrable in this given interval. Okay, so f is not Riemann integrable in this interval 0 to pi upon 4. Is it clear? So we have to check it. Got it? So how can we do this? How can we do this? Okay, let's check. So suppose you take a partition. Suppose you take a partition. So suppose you take a partition, let's say 0, pi by 4n, 2 pi by 4n, and keep on going till n pi by 4n, which is equals to pi upon 4. Okay, so we have taken this partition into consideration, and from here you have the rth interval as r minus 1 into pi by 4n till r times pi by 4. So what does your delta r comes out to be? Pi upon 4. Okay. Now see, since this is a piecewise function, and you know, every interval you have taken, what basically will be your cos, the LUB and the GLB of the function in that particular interval. See, it's very clear to see that since the function f is piecewise between cos function and sine function, so we basically know that sine function basically within an interval within the given interval 0 to pi by 4, the value of sine increases, right? The value of sine increases, but the value of cos decreases. Is it clear? Within the given interval 0 to pi upon 4, the value of sine increases and the value of cos decreases, right? So by this particular concept, we can obviously say that the GLB of this given interval is the sine of the smaller value, because this will be the least value in that interval, because sine is increasing. So sine will take the lowest value at the starting of the interval, right? So this is sine of r minus 1 times pi upon 4n. And what will be the LUB of the function in the given interval? The LUB of the function in the given interval, since cos is a decreasing function, so it will take its maximum value at the starting point of the interval itself. So it will be cos of r minus 1 times pi upon 4. Is it clear? Got it? Okay. Now, what is your LFP gonna be? So LFP equals summation r equals to 1 to n sine of r minus 1 pi upon 4n times delta r. What's your delta r? So it's obviously pi upon 4n itself, right? Pi upon 4n. Okay. So pi upon 4n comes outside, and inside you have sine of 0 times pi upon 4n plus sine pi upon 4n until you have sine n pi upon 4. Clear? This is what you are having here. Okay. Now see this, when let me give you an important formula which we will be requiring here, is that if you have a certain function of this type, sine a plus sine a plus d, this is a note, okay, plus sine a plus 2d, and we keep going till you have sine nd, let's say. Okay, so in this case what you can do is that In this case, what you can do is that, I mean, the formula of this particular summation comes out like this. You have sine times a plus, I mean the first angle times the last angle. Okay, so sorry, this is a plus n minus 1. So a plus n minus 1 times d divided by 2 times sine nd by 2 divided by sine d by 2. Clear? Clear? Okay. Now see, this is 1. I mean this is 0, right? Sine of 0 is 0, right? So we take from here to here, right? So you are gonna get here n terms, right? Taking the first one into consideration, you are gonna get n terms, right? So basically what happens here is that this particular summation which you are getting in the LFP, it just transforms itself into, so you can write the, okay, let me change the color. So you can write the LFP as pi upon 4n times sine of n minus 1 times pi upon 4n by 2 into sine n pi by 4n by 2, right, divided by sine of pi upon 4n by 2. Clear? Now calculating this, what you get, let's see first. Okay, so here you have sine of n minus 1 pi upon 4n by 2, right? So you can write this as sine of 1 minus 1 over n times pi upon 4 by 2. This is sine of pi by 8, right? And here you have sine of pi upon 4n by 2. Okay, so what you can do is that you can multiply a 2 there. Okay, so you can obviously write this like this, right? Sine of 1 minus 1 upon 4n pi upon 4 by 2 times sine of pi upon 8 upon sine of pi upon 4n by 2 by pi upon 4n by 2, right? And you multiply a 2 here. Clear? Is this okay? Is this okay? Is this okay? So this comes out to be, now see, now your lower integral, which is 0 to pi upon 4 fx dx, it's basically limit n tends to infinity LFP. And see, if you apply limit n tends to infinity here, if you apply limit n tends to infinity here, so this becomes sine of pi upon 8, right? So this becomes 2 sine pi upon 8 times sine pi upon 8, and limit of this particular value is 1, so this is sine 2 sine square pi upon 8, right? Which you can write as 1 minus cos of pi upon 4, which is 1 minus 1 by root 2. Okay, okay. Now in the exact same way, find the UFP, and I am giving you the formula to find the UFP. Note that if the same thing happens in case of cos function, cos a plus d till we have cos a plus n minus 1 times d, this comes out to be cos a plus a, the last term, just as we were doing in the sine case, right, times times sine nd upon 2 divided by sine of d upon 2. So use this formula to find the UFP, and what you will be getting as a result is obviously that your that your upper integral won't equal the lower integral. Okay, your upper integral won't equal the lower integral. your upper integral most probably will come out to be 1 over root 2. So they are not gonna be equal. Clear? Okay, I'm leaving this lecture till this much, guys, because I'm not well basically today. In the next lecture we will be starting with the further theorems related to Riemann integral. Then we will be moving on to Darboux theorems, and we will be going on with this topic. So meet you guys in the next lecture.